So far, we've been talking about just one gas at a time. What happens when we have a mixture of gases? One of the things we can use is Dalton's law of partial pressure. That tells us that the total pressure of a mixture of ideal gases equals the sum of the partial pressures. In other words, individual pressures of each of the gases that make up the mixture. So we could write it in equation form. P total, the total pressure, is equal to P of A, that is pressure of A, plus P of B, that is pressure of B, plus P of C, that's pressure of C, and so on until you've added up the pressures of all the gases. If we took 3 canisters of gas, one that had a pressure of 300 kilopascals, a second one that had a pressure of 600 kilopascals, and then a third one that had a pressure of 450 kilopascals, and we combine them together into one container, the total pressure in the container would be 300 plus 600 plus 450, making 1,350 kilopascals of pressure. Here's an example using Dalton's law. In a 10-liter vessel are 2.50 times 10 to the minus 3 moles of hydrogen gas, 1 times 10 to the minus 3 moles of helium gas, and 3 times 10 to the minus 4 moles of neon gas at 35 degrees Celsius. Part A says, what are the partial pressures of each of the gases? Part B says, what is the total pressure in atmospheres? To find the partial pressures, we're going to use the ideal gas law, PV equals nRT. We have a 10-liter vessel. Remember that gases take the volume of their container, so the volume of each gas is 10 liters. We know the number of moles of each of the gases. R is a constant. T, the temperature, is 35 degrees Celsius plus 273.15 to make 308.15 Kelvin. We're going to start by finding the partial pressure of hydrogen. We rearranged the ideal gas law to solve for pressure. The rearranged form that gives pressure by itself on one side of the equal sign is pressure equals nRT divided by V. The N for the hydrogen is 2.50 times 10 to the minus 3. The R value that we're using is 0.08206 liters atmospheres per mole Kelvin. Temperature is 35 degrees Celsius plus 273.15, which makes 308.15 Kelvin. Volume on the bottom of the equation is 10 liters. When we do our calculation, we get 0.006322 atmospheres of pressure for the hydrogen gas. Then we're going to use the ideal gas law for our next gas, which is helium. Again, we have the same rearrangement of the equation. This is all in the same container together, so the volume, that 10-liter vessel, is the same for all 3 of our gases. R is a constant, so that's not changing. The temperature is 35 Celsius, which is 308.15 Kelvin for each gas in the container. So the only thing that's changing for each gas is the number of moles. In this case, with the helium, the number of moles is 1 times 10 to the minus 3. But we plug in all the other numbers the same way as before, and we come out with 0.002529 atmospheres. Lastly, for neon, again we have the same rearrangement of the equation using the same variables, except for neon being 3 times 10 to the minus 4 moles. So we come out with 0.000759 atmospheres of pressure for the neon. We would say the partial pressure of hydrogen is 0.006322. The partial pressure of helium is 0.002529, and the partial pressure of neon is 0.00759. Although we use the term partial pressure, we use the full ideal gas law for each gas. Partial just refers to the fact that they are only part of the total gases in the container. The total pressure is just adding the 3 values for the partial pressures. When we do that, we come out with 0.00961 atmospheres as the total pressure in the container. When we have a mixture of gases, a common unit of concentration that we like to use is mole fraction. Rather than using molarity, which would be moles of a substance per total liters, we often want to find mole fraction, which is moles of a substance per total moles. We represent mole fraction with an X and we usually give it a subscript to denote which substance we are finding the mole fraction of. We'll just give it a generic A here. N sub A is moles of component or substance A, and total is all the moles in the mixture. The mole fraction of A is equal to the number of moles of A divided by the total number of moles. You can think of mole fractions sort of like a percent, except we're not multiplying by 100 to change to a percentage. We want to tell how much of the total is made up of a particular part. We can relate mole fraction to partial and total pressure. P sub A, the pressure of A, equals X sub A, the mole fraction of A, times P total, the total pressure. If we know mole fraction, which is like a percentage, we can multiply that by total pressure to get the amount of the individual substance. Here's an example. We have a mixture that contains 2.83 moles of oxygen, 8.41 moles of nitrous oxide, and the total pressure is 192 kilopascals. We're trying to answer two questions. What are the mole fractions of both of the substances, and what are the partial pressures of both of the substances? Let's start with the oxygen gas, and first find its mole fraction. The mole fraction of the oxygen is the number of moles of oxygen divided by the total number of moles. The number of moles of oxygen is 2.83. The total number of moles is the amount of the oxygen plus the nitrous oxide. So we have 2.83 plus 8.41 on the bottom. We come out with a mole fraction of 0.252. Again, we're not multiplying by 100, we're just leaving it in decimal form. However, if we wanted to think of it as a percentage, we could think of it as 25.2%. By the way, mole fraction is unitless. We're not going to say 0.252 moles or anything like that, just like a percentage doesn't generally have units along with it. The mole fraction does not have a unit with it, it's just a fraction. Next, we can take the mole fraction and multiply it by the total pressure to get the partial pressure of the oxygen. We multiply 0.252 by 192 kilopascals, and that gives us 48.4 kilopascals. That means that 48.4 kilopascals out of the 192 kilopascals is coming from the oxygen. We can do the same types of calculations for the nitrous oxide. The mole fraction of the nitrous oxide equals the number of moles of nitrous oxide divided by the total number of moles. The number of moles of nitrous oxide is 8.41, and again we have our sum on the bottom, 2.83 plus 8.41. It's only the top part that's changing as we go from one substance to the next within this mixture. We come out with 0.748 as the mole fraction of the nitrous oxide. The mole fractions should add up to 1, in other words, 100%. So another way that we could have figured out that the mole fraction of nitrous oxide is to take 1 and subtract the 0.252, which is the oxygen, and whatever is remaining must be the nitrous oxide. That would give us that same 0.748. Finally, we can find the partial pressure of the nitrous oxide by taking the mole fraction and multiplying by the total pressure. We take the 0.748 and multiply it by 192 kilopascals, and that gives us 143.6 kilopascals as the pressure coming from the nitrous oxide. In other words, the partial pressure of the nitrous oxide in this mixture. Another way we could have figured that number out is by taking the total pressure and subtracting the pressure of the oxygen. We know that all of the pressures should add up to the total, based on Dalton's law of partial pressure. So if we took the total pressure of 192 and subtracted the 48.4 that was coming from the oxygen, then 143.6 kilopascals must be coming from the nitrous oxide. A mixture of three gases has a total pressure of 1,380 millimeters of mercury at 298 Kelvin. The mixture is analyzed and found to contain 1.27 moles of carbon dioxide, CO2, 3.04 moles of carbon monoxide, CO, and 1.50 moles of argon, AR. What is the partial pressure of argon? 1 atmosphere is equal to 760 millimeters of mercury. Is it A, 0.258 atmospheres, B, 356 millimeters of mercury, C, 5,345 millimeters of mercury, or D, 301 millimeters of mercury? The correct answer is B, 356 millimeters of mercury. First, you're going to solve for the mole fraction of the argon by taking the moles of the argon, which is 1.50, and dividing by the total number of moles, which would be 1.27 plus 3.04 plus 1.50. Once you have that mole fraction, you multiply by the total pressure of 1,380 millimeters of mercury, and that gives you 356 millimeters of mercury, which is B.